Hello. Okay, so in this video, we're going to finally do the iteration. So far what we've done are just obtaining some estimates with a suitable test function, then making the choice of a test function. So now we have some kind of an estimate where we can work with an iteration scheme. So for this video, we actually carry out the iteration. So just to recall that the goal now is to find some big k such that this is true. And what that means is if you find such a k, then the positive part of u is bounded by this almost everywhere in b1 half. So this is in the ball of radius 1 half. And that is what we want to show, local boundedness. Okay, so let's proceed. Okay, how do we do that? Okay, so just some observations first. So let k0 be less than equal to k. So we have big K and H. Note that k0 is this sort of minimum k that we need so that the estimate would work. Okay? And we have 1 half to r. Okay. So we make the following observations. So the first one, so since if u is bigger than h, then you have that u must be bigger than k, obviously. So this then tells you that a of h r is contained in a of kr from definition. And this now tells you that the integral of u minus h squared on a of hr is less than or equal to u minus h squared a of kr because of this set inclusion. And this is less than or equal to u minus k squared a of kr. And the reason is, so if you have k, h, u, the distance between h and u is smaller than the distance between u and k. Okay? Okay, so this is the first observation. The second observation, oops, wrong color. Okay, the second observation is this. Okay. So the measure of a of hr, this is the measure of the set where u is bigger than h intersect br. So this is just the same as, I'm gonna subtract k on both sides and note that this is still positive. Intersect br. So this is the set, the same as the set where u minus k over h minus k is greater than 1, intersect br. Okay, so that implies then that a of hr, so this is equal to u minus, what do I have there? U minus k over h minus k bigger than 1 br. So this is less than or equal to u minus k over h minus k squared in this set. U minus k h minus k br, because this is bigger than 1. Okay? So this is just 1 over h minus k squared integral over a of kr not yet. So note that this is less than or equal to a of kr because this is positive. Okay? So that instead of equality, we have less than or equal to, and this is now u minus k squared a of kr. And I invite you to actually like verify the calculation. So that's going to be like good practice. And again, I do hope that when you watch this, you have a pen in hand so that you sort of do the calculations together with me. Yeah, and this is sort of why I'm doing this too. Like I'm sort of trying to like write out the details that otherwise isn't written in the book. So yes. Okay, so we have these two observations. So what are they? We have that this is less than this, and that this is less than that. Okay. Now, let's look at the estimate that we have before. The estimate that we have before is this one. And remember that this is true for k bigger than some k0. Okay. So, let's write that as, so we have integral of u minus h squared a of hr less than or equal to some constant c times 1 over r minus r squared integral of u minus h squared a of h big R. So instead of k, I put an h. H is bigger than k0, plus h squared plus f squared times a of hr raised to epsilon. And I factored out this one. Okay? Oops, sorry. So this is just that, and this is epsilon. Okay. So from the observations that we had before, I know that this is less than or equal to u minus k squared a of kr. And what else? These are less than or equal to 1 over h minus k squared times u minus k squared a of kr. Just from the observations that we had before. Okay. Okay, so remember, what are we trying to do here? We're trying to set up an iteration scheme which would give us the k that would give us local boundedness. Okay. So with these controls, we then have less than or equal to some constant c. I have 1 over r minus little r squared plus, so I can factor this out. And then I'll be left with this plus h squared plus f squared over h minus k squared multiplied to 1 over h minus k to the 2 epsilon. Where did that come from? Wait, let me see. Oh, it came from this term here. Okay, multiplied to the thing that I factored out. Squared a of kr. And I have here 1 plus epsilon because we already have something to the epsilon because of this term. Okay, so we have that. So taking square roots, we get u minus h positive part L2 b little r less than or equal to some constant 1 over r minus r. So you take square roots, it's gonna be less than a constant, plus h plus f over h minus k. So this is some kind of an analysis cheat. Like, you know that the square root of this is not h plus f, but you can control it by h plus f, and that is fine. Like in analysis, we mostly work with inequalities rather than equalities. Okay, so that is fine. Times 1 over h minus k multiplied to L2 norm of u minus k positive part in big R. Okay, so let's see. This is important. We have here large h. H is larger than k, but little r is smaller than big R. So remember our figure from the first figure. So we have here the L2 norm of u over parts where it's big, and these are parts where it's bigger than h. And here we have the L2 norm of u where it can be a bit smaller, it's bigger than k instead of h. Here we're looking at the parts where u is big in a smaller set br compared to this, which is over a bigger set, b big R. Okay, so this is the estimate that would that we work with in order to apply that iteration scheme. So just some notation, I am gonna call this phi of h little r. So this is phi of k big R. So what we have is phi of hr is less than or equal to c 1 over r minus r plus h plus f over h minus k, 1 over h minus k to the epsilon times phi of kr to the 1 plus epsilon. This is big R. Okay, so this is what we have. Again, big H bigger than H bigger than K, little r bigger than smaller than big R. This is like L2 norm where U is big in a small set controlled by where it can be a bit smaller over a wider set. Okay, so now what we're going to do is in order to obtain some kind of an iteration scheme, we need to produce a sequence K sub L and R sub L, where the K sub L would converge to the K that we want, that we don't know yet, to the K that we want, and R sub L would converge to 1/2. So let's just like note that. So we choose a sequence where the K sub L would converge to the K that we want, meaning to say this is the K for which U plus almost everywhere in B1/2, and R sub L would converge to 1/2. Okay, so this is what we want, because this is we sort of want this to converge to phi of that K, R is 1/2, and we want to show that that is equal to 0. Okay. So how do we do that? Okay, so the choice of KL would be is equal to K0, the minimum K, so that the estimate would always hold, plus this K to be determined times 1 minus 2 to the L, where K positive TBD, to be determined. Okay. And R sub L would then be tau. So tau is just 1/2. Tau plus 1 over 2 to the L, 1 minus tau. So note that K sub L is increasing and R sub L is decreasing. Okay. And this is just algebra, but K sub L minus K sub L minus 1, this is what? K over 2 to the L. And R sub L minus 1 minus R sub L, this is 1 over 2 to the L, 1 minus tau. So just some algebra. Okay. And now we apply it to our estimate. Do I want to do it here? Let's do it next page. So applying now the estimate that we have, which was given for arbitrary H, K, little r, and big R, to R sub L, K sub L's, what we have is phi of bigger K, smaller r, less than or equal to some constant, 1 over bigger R, smaller r, plus bigger K, smaller K, bigger K, smaller K to the epsilon times phi of smaller K, bigger R to the 1 plus epsilon. Yay! So we have this. Okay, so this is nice, and this is sort of something common in analysis. You have some kind of a sequence, and you have that this is less than or equal to something previous, something at like the previous step. So the idea is you can sort of iterate it so that you reach phi of K0, R0. So we'll see. We're not gonna get exactly that because it's a bit messy, but we'll see. Okay, so let's sort of work with this nasty bound. Okay, so we have already calculated what are these differences. So we already know what these are. So plug in those in, what do we get? So we get C 2 to the L, 1 minus tau, plus 2 to the L, K0 plus K plus F. It's actually K times 1 minus 1 over 2 to the L. But note that this is less than or equal to K. So just make it K and therefore this is not equal but less than or equal. K plus F over K times 2 to the epsilon L over K to the L. Note that here L is from 0, 1, 2, and so on. Times phi of, what do I have here? K to the L minus 1, R to the L minus 1 raised to 1 plus epsilon. Okay? Let's factor out the 2 to the L, and then this is just algebra. This is, you can show that this is less than or equal to some constant times constant over 1 minus tau times k0 plus k plus f over k to the 1 plus, wait, this is not L, I'm sorry, this is epsilon. Okay, so I have there k to the 1 plus epsilon times 2 to the 1 plus epsilon times L times phi of k L minus 1 R L minus 1 to the 1 plus epsilon. Okay, so remember, okay, so what do we have here? We know that k sub L converges to k0 plus k, some big k, and hopefully this is the k that we need, okay, that would give us the bound that we want, and we know that this converges to 1/2. So the hope is, as L goes to infinity, we need to show that the bound goes to 0 as L goes to infinity. So that's the goal, that this can be dominated by something that goes to 0 as L goes to infinity. Okay, so what I did first, so the book does it by induction. The next step is gonna be an induction step. So I was thinking, let's not like do the induction. Let's see if we can iterate this. Like this is gonna be less than something. I have now phi k L minus 2 R L minus 2 raised to what? 1 plus epsilon times 1 plus epsilon. But it, and then sort of do this up until you reach phi of k0 R0. But it was hard. It was very messy. Okay, so what we do instead of doing that is, well, I want this term to go to 0. So I want to bound it by something that I know would go to 0. Now, eventually, the estimate should be in terms of phi of k0 R0, because it's very natural. You sort of like iterate it. Eventually, you would reach k0 and R0. But aside from that, we want that control to go to 0 as L goes to infinity. So the conjecture is, so for every L, okay, there exists gamma bigger than 1 such that for every L, we have that phi of KL RL is less than or equal to phi of K0 R0 over gamma to the L. Because if such a thing is true, you know that this would now go to 0. This would go to phi of K0 plus K 1/2. So this is the K that you're looking for. Okay, so how do we prove this? So again, we started with something like this. I was saying that it's hard to sort of like do this again and again until you reach R0, K0, R0. So what you want is, okay, let's just conjecture the thing that we want to happen. And what we want to happen is that this is controlled by something that would go to 0. So we have here phi of K0, R0 because it's natural that the control would have this term, as evidenced as by if you just iterate this many times. So this would appear eventually. So over something that would go to infinity as L goes to infinity. So that would be something like gamma to the L for some gamma bigger than 1. So we prove this by induction. Okay, so moral of the story here is you don't need to like do this up to 0. You just sort of conjecture the thing that you want to happen. Okay, so for L equals 0, it's clear because you have phi of K0 R0 and that is equal to phi of K0 R0 over gamma to the 0. You can, yes. Okay. So this is sort of independent of whatever gamma is, as long as it's not zero. Okay, so it's good. Okay, so suppose that it's true. So suppose that you have the phi of kl minus 1 rl minus 1 is less than or equal to phi of k0 r0 over gamma to the l minus 1. So we need to show it's true for l. Okay. Okay. How do we do that? Okay. So note that we know that phi of KL RL would be less than or equal to a bunch of things times phi of KL minus 1 RL minus 1 raised to 1 plus epsilon. And this is sort of like the tricky thing, this 1 plus epsilon thing. So let's work with that. Okay? Okay, so let's work with that. So I have phi of KL minus 1 RL minus 1 to the 1 plus epsilon. By assumption, by the induction hypothesis, this is less than or equal to phi of k0 r0 over gamma to the L minus 1 raised to 1 plus epsilon. And what is this? So let's separate out this over, I have, so this would become what? It would become gamma to the L minus 1, 1 plus epsilon. And what that is gamma to the L plus epsilon L minus 1 plus epsilon. Is that true? For gamma L epsilon L minus 1 plus epsilon. Okay, so I can write this as gamma to the L times phi of k0 r0 to the epsilon over gamma to the epsilon L minus 1 plus epsilon. Okay? Okay. Okay, so we have that. So now let's prove what we want to prove. So what we want to prove now is, let's erase some stuff. Move it there. So what we want to prove is, with this term here, KLRL. So by the estimates that we've derived, this is less than or equal to some constant over 1 minus tau times k0 plus k plus f over k to the 1 plus epsilon. Is that what I have before? Yes, okay. Times 2 to the 1 plus epsilon times L. Times phi of KL minus 1 RL minus 1 to the 1 plus epsilon. So now we're going to replace this term by this term. So to save space, I'm just going to erase that. And then so we just replace it with this term. So let's just copy or write it as phi k0 r0 over gamma, what do I have there? Okay, just write it as this. So gamma epsilon L minus 1 plus epsilon times phi of k0 r0 over gamma to the L. Okay? Okay. So again, what's the goal? The goal is to show that this is less than or equal to this. So we need to show that there is some choice of gamma and actually k such that this is less than 1. Okay, so I'm gonna write this. How do you say? Behemoth, whatever. I'm gonna write this as c to the gamma 1 plus epsilon over 1 minus tau. Where did that come from? It's this part. Boop. Times k0 plus k plus f over, let's write this as 1 plus k0 plus f over k. And then the k to the epsilon, I'm gonna combine it to some place else. Okay? Oh, this is supposed to be epsilon. Boop. Okay. So times 2 to the 1 plus epsilon L over, I have gamma to the epsilon L times phi of K0 R0 over K to the epsilon. Where did that come from? It's this term and K to the epsilon. So it's just algebra, and I hope that you're also trying this together with me. So we have that times phi of K0 R0 over gamma to the L. Okay. So now, to simplify things, I'm gonna choose gamma such that gamma to the epsilon is equal to 2 to the 1 plus epsilon. And note that, so what is that? Gamma is equal to 2 to the 1 plus 1 over epsilon. This is bigger than 1. Okay, now we have a gamma. So with this choice of gamma, okay, what do we do now? We still have a free parameter, which is k. So now you can choose k so that this whole thing now is going to be less than 1. So with this choice of gamma, this is equal to 1. Now, so this is just fixed. It doesn't depend on L. This is independent of L. This can be made small. So this can be made small, like 3/2 or something. And this doesn't depend on L. This is also independent of L. So is it fair to say that you can choose K, which is of the form C star of K0 plus F plus phi of K0 R0 for some C star large? Because for such a choice of K, it kills this term. It dominates this term. It makes this term small. It also dominates this term, so it makes this term small. Okay, so it's easy to see that for a big C star, this choice of K would make this whole term less than 1. Okay, so for such a K, and know that that is going to be bigger than K0. So for such a K, note that that is bigger than K0. You have that phi of KL RL is less than or equal to, so for such a K, this thing is gonna be less than 1. Okay? And then now you have phi of K0 R0 over gamma to the L, which is what we want to show. So now with this, what you do is let L tend to infinity. So note that this is an L2 norm of something, and it's fairly straightforward, the big dominated convergence, and I invite you to try it, that as L goes to infinity, you have phi of, this is K0 plus K, 1/2. This is the limit as L goes to infinity of phi of KL, RL, because KL converges to this, RL converges to 1/2, less than or equal to limit as L goes to infinity of phi of K0 R0 over gamma to the L. Excuse me, and since gamma is bigger than 1, this limit is 0. So what is that saying? This is telling us that the integral of u minus K0 plus K squared over over a of K0 plus K 1/2 is 0. So that this tells you that u is less than or equal to K0 plus K almost everywhere in B 1/2. Or that this positive part, sup of u plus in B 1/2 is less than or equal to K0 plus K, but in fact K, remember that the choice of K sort of depends on F, which is the LQ norm of little f, and phi of K0 R0, which is like the L2 norm of U plus. So I invite you to do the algebra, but you get the result that we want. So U plus L2, L2 B1 plus LQ norm of F B1. And there you have it. Okay. So what we're gonna do next is either look into Moser's approach and see that more or less they're kind of the same. So in Moser's approach, instead of looking sort of these like truncations of U, we sort of get a reverse Hilder inequality. Like you get the LQ norm is um, controlled by an LP norm where P is smaller than Q because usually you have the other direction. And it's also like an iteration scheme, but what Han Lin is saying is that more or less it's the same. So either we look into that or we now show that we actually have Hilder continuity because at this point we've only shown local boundedness, and that's the difficult part. And then maybe show how to prove how to solve Hilbert's 19th problem. Maybe we can do that. I was also thinking of maybe we could also look into weak solutions of the Navier-Stokes equations. So that could be also fun. Or I was also sort of in the mood of doing viscosity solutions. So that is also fun. So we'll see. But thank you for watching.